Okay, so as it's the last lecture, maybe I should just say something very brief about exams. Dates for the written exams have been published for a long time on the webpage. Some of you have signed up for one of the exams. If you're going to take one of the written exams, you have to sign up for it on this before the deadline for signing up to the exam. Then pass the practical side of the course, which is your combined, the higher of your marks from exam mark only or exam mark combined with the quiz mark. You pass the side of the course, you get invited to come to the oral exam. So the oral exams will start as soon as the written exams have been marked. So I don't know exactly what date that will be, but it will be getting towards the end of June, I guess, last week of June or something like that. Don't quite remember Gregor's availability for marking. And there'll be a form to sign up online, so you sign up for your exam, and they take. So that will be announced by email. So sign up online. Be announced soon. And also, before the oral exams take place, I'll publish a page on the course website that gives more information about what the oral exam, what the format of the oral exam is going to be. So what the questions are going to be, and what combination of questions you're expected to ask. Sorry, you're expected to answer, not ask. I'll ask the questions, but I haven't completely finalised my ideas about that yet. But anyway, the information's been there. So in good time. So information is published in due course. And if you pass, once you've passed the written exam, there's no, as I say, the oral exams will start as soon as the exam marks are available, but there's no necessity to take the oral exam immediately if that conflicts with your other constraints. So if you want to get the marks this year, the only constraint is you have to take the oral exam by the end of the first week of September, because I'm away the second week of September. And there will be several periods, different periods for signing up to taking the oral exam, some in June, some in July, some in August, and the first week of September. Okay, are there any questions about that?
Yeah, I have a question.
Yeah.
So about signing up online, doesn't make sense to me that we can sign up before we even know which slots are available, given that they will be available only after the written exams.
Sorry, no, the slots will be available before the written exam results are available, and okay. I'll probably even do that quite soon.
Okay.
And I think you can sign up in the expectation that you're going to pass the exam, and if you're unlucky in the exam, then okay, well, you can just vacate that slot.
For example, if I'm planning on passing, and
should I pause the video?
No, it's okay. It's okay. So
yeah,
I'm planning on passing, and I see the written exam on the 10th. Okay.
Yeah.
And I plan on having. I would like to have oral exam on the 15th. So is that?
Oh, I see. But
yeah,
the exam will have to be marked.
Yes, that's.
So I need to check with Gregor what the earliest we can mark the exam is. And I vaguely remember from discussions with him a long time ago that there's the holiday period involved there, so might not be able to have the exam.
Yesterday he assured us, just the information. Yesterday he assured us the exercise that for the first exam he will mark it almost immediately. So he will make sure that it's done as quick as possible for the first.
Okay, well I shall discuss this with him, and the available exam slots will be clear in the signing up form published, and you are welcome to sign up before you know your exam results. So and that goes for everyone. Any other questions?
Yes. This is if we pass now, we can take oral in September.
Yes, you can. But only the first week. And if you want the mark this year, it has to be the first week of September, because I'm away the second week, and the mark deadline for this year is the second week.
Okay.
So there's only 1 week of opportunity. Any other questions? Okay, good. So right. So today's topic, let me remind myself. I mean, I know what the topic is, I just don't remember what I called the title. So I've named it ZFC, famous theory of mathematics that most mathematicians still consider the axiomatic basis of contemporary mathematics, and independence results. These are results such as that the continuum hypothesis is independent of the axiom. That theory, we cannot prove the continuum hypothesis, and we also cannot refute the hypothesis from the axiom. Essentially, ZFC part is about how to construe the axioms of set theory that we've been working with informally as a precise formal axiomatic theory. I've already said what the independent results is about. And I guess many of you have seen axiomatizations of ZFC before, for example, in logic and logic. So that, of course, typically ends by discussing the axiomatization of ZFC. So we're going to revisit that material, but I'm going to approach it from a slightly different angle. And that I'm going to begin with by giving a formal axiomatization of the theory, the set theory that we have been informally working with throughout the course, which isn't quite ZFC. And then I'll say what ZFC is, which is 2 more axioms on top of the theory that we've been informally working with. In both cases, we want a formal theory, and so the formal theory is going to consist of a set of axioms, and the axioms are going to be formulated in what's called first order logic or predicate logic. And in order to formulate axioms in first order logic, you start off with a language, which is signature, things you can talk about. So we need an appropriate language for the concepts we've been using in the course. I guess most of you have seen first order logic somewhere before. Doesn't matter for this lecture if you haven't. So we're going to have a formal language in which properties can go over here. So we're going to have a formal language. That means a precise language with precise rules for generating it, just like programming languages are formal languages. A formal language in which formulas in this language are just like a program is the main concept in programming language, and sentence is maybe the main concept in natural language, and in set theory, well, first order languages, formulas are the main concept. So formulas of the language express properties of the mathematical universe, which is our mathematical universe, which, in contrast to the mathematical universe of the Mallet-Frankel set theory, our mathematical universe is allowed to contain elements that are not sets. That's how we start the course beginning, actual one. So properties of math. And what primitives, what basic concepts, that is, do we need to express properties of the mathematical universe? Well, formulas are given by just some simple rules for generating formulas. So formulas, phi, I'm going to use phi and psi and so on, range over formulas. So are constructed using the following rules. So first we have well, I'll just say R, and these are the rules for giving them. So we have some variables, and variables represent entities in the universe, so set or non-set, as it were. And we have one kind of formula is an equality between variables. So I'll put bullet points in front of the different formulas. That the bullet point's not part of the formula. So we're going to have another formula, which is, so these are called atomic formulas because they don't have any logical structure. Another basic formula in the language of set theory is formed using the membership relation. So this says entity X in our universe is a member of entity Y. And for this to be the case, Y necessarily needs to be a set. So it basically says Y is a set and X is a member of Y. And we're going to have further formula. So I'm going to write S of X, and we interpret this as saying X is a set. So entities in the universe need not be sets, but we have a way of saying that an entity in the universe is a set. When we go to another Frankel set theory, we won't need this anymore because it's another Frankel set theory. The universe consists only of sets. And then these are our atomic formulas, and first order logic just has rules for building more complicated formulas out of first order formulas, sorry, out of atomic formulas, which are close off the formulas under the connectives of propositional logic and quantifiers. So we also have a formula for conjunction. I'll stop writing the bullet points. Maybe these are three ways of doing atomic formulas, various ways of doing non-atomic formulas. So we have conjunction and disjunction, or implication, implies, if and only if, by implication as it's called, and negation. And obviously, some of these are redundant in that they can be expressed in terms of other ones. And the other important thing we have is quantifiers. So we can quantify, we can say for all X, phi holds, and there exists a phi hold. And in each case, remember our variables are ranging over elements of the universe, so sets or non-sets, and we're just saying for everything in the universe, phi holds, or there exists something in the universe, phi hold. And that's it. So all we need are the formulas we can build up using these rules. It's very minimal, and it's amazing that it's as powerful as it is. And then our axioms are going to be, well, actually, so I said, in natural language, sentence is the kind of linguistic entity, an important entity. So also logic formulas are important, but our axioms are actually going to be, sorry, not finite, but our axioms are going to be a set of sentences expressing the basic axioms we have for our universe. So a sentence in this case is a formula that does not have any free variables. That is a formula in which every variable occurrence in the formula is within the scope of one of the quantifiers bounding that variable. So sentences are formulas with no free variables. The point of the sentence is it should, in any universe in which we're interpreting the formulas, the truth or falsity of a sentence should be determined by the universe alone, and because there are no free variables, it's independent by the meaning we're assigning to the variables. But if you have a formula with a free variable, whether it's true or not depends on what entity you attach that free variable. Okay, so in order to state the axioms, we could just use exactly these formulas, but it's useful to have a few abbreviations. So I'm going to introduce some abbreviations. It would be even useful to have more abbreviations, but I want to introduce some abbreviations that are a little bit interesting. So the first abbreviation is we're going to define, going to give abbreviations for what we mean when we use bounded quantifiers. So we're bounding quantifier by rather than quantifying over all elements of the universe, we have some y which we want to be set, and we're saying we're only requiring y to be true for all x to y. And so this I'm going to interpret as meaning that y is a set, and for all x, if x belongs to y, then y holds. And what do I need to do to change this to do the existential quantification? What do I need to change here?
Well, you're going to have n instead of. Right?
Yes. So change the rule to exist, but also this should be a conjunction. And I'm sure you've met this kind of thing before, but it's important to understand why that's the case. Okay. And then the more interesting abbreviation I'm going to use is the following. I'm going to write it like this: a backwards S, X. Think of this as like a form of quantifier. Phi. What this says is there exists a y such that y is a set, and for all x, y holds if and only if x belongs to y. Okay. So we're importantly here, we need to choose the variable y so that it is not one of the variables in the free variables y. But in fact, I'm just used the term y scratch. Can anyone articulate what this means?
Well, there is, maybe I'm wrong, but I think that this guarantees that there is a state instantiating the formula.
Yeah, what does it instantiate?
Well, all of the elements in the state are going to be precisely those elements for which the formula holds.
Yeah. So the elements that satisfy phi. So if you, in general, for a formula, we're thinking of phi as expressing a property of x. And in general, for a formula, the x that satisfies formula phi will form the proper class. For example, if phi was the formula x equals x, it would be everything in the universe, and that's a proper class. And what this is saying is there are set many x satisfying phi, or there is a set. The elements satisfying phi form a set rather than a proper class. But one could think of it as kind of, we had intuitions about sets in the first lecture, and think of sets as kind of small things. And so this is like saying there are only set many x satisfying phi. And so it's written like this. This is not my notation. I first saw this in works by someone called Peter Axel. Written like this, just in the same way that universe is plural and exists last to reflect your rotated versions of the letters. So this is the reflected version of the letter S being a set. Okay.
But why do you require y to be reversed?
Because if y occurred in the formula phi, this wouldn't say what you think. Think about that. So we can talk about it during the break, but it needs to, if y occurs in the formula phi and we use the same variable phi here, we end up saying something different. So what really thing you actually say depends on the formula. I guess. Okay, so let's do the axioms of the set theory we've been using in this notation. Axioms of set theory traditionally start with the axiom of extensionality, which tells us, well, we'll remember the axioms. So I just write X for extensionality. Right, remember what it says from the first lecture and also from Logika in Norsitzer. So if two sets have exactly the same elements, then those sets are equal. So we need to formulate that by saying we've got two sets, and if we've got two sets and they have exactly the same elements, so for all Z belongs to X. So for all Z in the universe, Z belongs to X, if and only if Z belongs to Y. Then, well, if that conjunction holds, then X equals Y. And I told you that axioms are a list. So the axioms are sentences. We're going to have a list of sentences. So strictly speaking, let's put it in orange. This is really the true honest axiom is for all X, for all Y. Then this is true. And we need to say that X and Y are sets because it's not true for arbitrary things in the universe. Because if you take suppose numbers aren't sets, if you take two different numbers, each of them will have no elements, but they're not equal to each other. So that they would be made equal by this axiom if we didn't restrict this axiom to set. There's extensionality, the principle by which we identify sets. And actually, because we've got the potentially non-sets in the universe, we need another axiom beforehand, membership axiom, which enforces that constraint that I said when I introduced what membership means. X member of Y means that Y is a set and X the member of Y. So we need an axiom stating that. Again, for all X, for all Y, if Y belongs to X, then X. Okay, and then we can go on with the axioms of set theory that we've met before. So separation, I'll just call it that. So separation, you'll remember, said if we've got a set and we have any property, then the elements of the set satisfying that property, a class of all such things, themselves form the set because they're bounded above. We're making a sub-collection of the starting set, and separation said that sets are closed under sub-collection. So that's easy, again, for all X, but I won't write all the quantifiers. Well, it's easy, except, well, we can say it. We want to talk about, if we've got a set X, then for any property phi, the elements of X satisfying phi themselves form the set. So to say they form the set, we can use the set many quantifier. So this gives us a nice convenient formulation of this axiom. So there are set many Y such that Y belongs to X. And how's the property given to us? Well, the property can be given to us by any formula. So this is actually what's called an axiom schema, in that it's an infinite set of axioms, one for every formula phi. The formula phi is allowed to contain free variables, but if it does contain other free variables, then we need to include those free variables in universally quantified variables on the front to make it safe. Once again, to avoid saying silly things, y needs to be a variable that's different from x and doesn't occur in phi. So again, we want y to be fresh. And then we had a basic rules for building sets. One was that the empty set is a set. I'm not going to write that down because it's going to follow from the infinite set, from the axiom of infinity and the axiom of separation. Once we've got some set, we can restrict it to the false property and we get the empty set. Consequence of the axiom of separation. Yes, go
I didn't interrupt, but why here isn't fresh in this point? Because it occurs in the formula we're binding.
Ah,
yeah.
Yes, you're right.
So we need
another So
not just simply the freshness.
No, we don't need any condition at all. Yeah, exactly. Just right. I'm confusing with right. Yes, I'll think about whether we need a condition during the debate, but you're completely right. Shouldn't. So I added these constraints yesterday, and that wasn't definitely needed here.
Yeah.
Anyway, so we had the axioms for building up sets, so that was a good catch. We had the empty set, as I said, that's not needed. We have the pairing axiom, which says for any x and y, we've got the unordered pair, the set that contains just the elements x and y. So we can simply say that for all x, for all y, there are set many z such that z equals x or z equals y. We've got the power set axiom, which says for any set x, there's a set of all subsets. So there are set many subsets of set. So once again, we can formulate that in a convenient way using this quantifier for there are set many elements. So this says if x is a set, then there are set many y satisfying the property that, well, satisfying what it means to be a subset of x. So that is, there are set many y such that y is itself a set, and y is a subset of x. And of course, we could introduce notation for subset and define that. And that should go on this board. But let's make everything as put everything in as primitive terms as possible. So let me just say, for all z in y, z belongs to x. Well, that's y is a set and it is a subset of x. And then we have the axiom of union and the axiom of replacement. And these two can be wrapped up nicely together in an axiom saying that the universe of sets is closed under indexed unions, which has a very neat form. So I call this indexed union, just in union here. So this says if x is a set, that's our indexing set. And if for all y in x, that's for all indices y, there are set many z such that phi holds. So now, phi is a formula that's giving us an index, that's serving to give us an index family of sets indexed by the set little x. and we know that for each little x we get a set because of this set many quantifier here, then in that case, the collection of all elements that arise in this, the index union of all the sets of all the z's, so namely all those sets that arise from some y sub z, or the collection of all z's that arise from some, the collection of z's that arise from some y via phi itself forms a set. In other words, there are simply set many z for which there exists a y in x such that phi. Yep, that's right.
Excuse me. About the power set. I might be missing something, but just seems to say that there is some subset X. That's one issue, and the other by itself.
But it's not saying that y is a set. There are set many y, but there's this kind of space here. Maybe I should use punctuation like a dot or something. This property forms a set. So the collection of all y, all those y that are themselves set and subsets of x is a set. So that's exactly per set.
Okay, yeah, sorry, I was mixing up the two because there you have x, well, y and x, the y is playing a different role here, so yeah, I just got the thank you.
Yes, okay. And lastly, the axiom of infinity. The axiom of infinity, I'm going to formulate as there is a set closed, which I think was one of the formulations in the lectures. There is a set closed under, well, containing the von Neumann zero, which is the empty set, and closed under the von Neumann Besser operation. So there exists an X such that it contains the empty set. So there exists, we haven't given ourselves notation for the empty set, although we could. Let's just put it in let's write it out using basic notation. So there exists a y in X that's empty, so such that that's the empty set. So y is a set, so such that y is a set, and for all, well, and that it's not true that there exists a z such that z belongs to y. That's saying exists a y in X that's the empty set, and moreover, for any z in X, oh, sorry, for any y in X, we're going to have von Neumann successor. I'm going to put all y's in X are in fact set, which isn't in the notes, but there's no harm in doing it. So y is a set, and there exists a z, which is going to be the von Neumann successor. So there exists a z also in X. Then X is closed in the von Neumann successor. So being the von Neumann successor means that z is the union of, sorry, the von Neumann, we want to say z is the von Neumann successor of y. So z is the union of y together with a singleton y. So in other words, we want to say for all w in z, either w equals y, so that's actually want to say that we want to say that z is that union. So we say for all w, we want to characterize z as being exactly that union of the singleton y together with the y itself. So w belongs to z if and only if either W belongs to Y, so this is the being in Y union singleton Y, so either W belongs to Y or W equals Y. Okay, so that's a bit of a mouthful, that axiom, to formulate. Anyway, it does the job. Those axioms are all the axioms we need to do essentially the mathematics of the course until we get to the axiom of choice. So this, just to write it down here, as I said, this acts as an equivalent. This is equivalent to the combination. The index union is equivalent to the combination of union and replacement. It's nice because we don't need to talk about class functions. Okay, so these are the axioms. What's the benefit of having a formal axiomatization? Well, once we have axioms, we can subject the axioms to have precise proof rules for first order logic. So we have given an axiomatization, we then have a precise notion of what it means for a sentence in the logic to be provable from the axioms. So the axioms give us give a precise notion of formalized proof, formal proof, using precise proof rules, which I'm not going to go into because that's not the point of this course, but precise proof rules for first order logic. And for any sentence I, we can ask, do we have axioms turnstile, which means the axioms turnstile sign. So what the turnstile means is it the case that we have a correct proof that's a proof following the rules of first order logic of the form of the sentence guide from the axiom. And if you have such a proof, it can be given very precisely, written in very precise terms. And you write proofs in them, and the computer checks that you've given the correct proof. So you have a proof, a computer type it into a computer, the computer check that the proof is correct for you from axioms. And the amazing thing is that, I mean, apart from sometimes we use some other axioms, like the axiom of choice and variants of it, but if one uses those, one adds further axioms. So the amazing thing is that all the results in this course are provable from the axioms. Plus additional actions where needed. Except there's a bit of a caveat here, because the formulation I gave for set theory, we started off with the notion of class, and we have quite a few results about classes. So, for example, we had an early result was that there is even before the axiom of infinity, there is a natural numbers structure as a class. But then, more importantly, there is then there exists an ordinal structure. An ordinal structures are necessarily a class. There's no axiom that we can't have an axiom that tells us that the ordinals form that. So there are results like this which involve statements that there exists a class with some properties. So those also make sense from this axiomatization, but results about classes have to be understood as meta-theoretic results in the following way, that whenever we've proved the existence of a class, it's always the case that our proof, what it does, is not a proof of a formula in the logic from the axioms. What it is it's a construction of a formula that represents that class. So our proof constructs a formula that you can then prove from the axioms that that formula has the properties that we have ascribed to the class. And similarly, when we constructed a class function, again, the proof that a class function exists amounts to constructing a formula with two variables. And again, you can prove from the axioms that that formula with two variables is a class function. So there's just that slight issue in going between the axioms here, in which we can't talk explicitly about classes because the variables range only over elements of the universe. And in our informal development, we were talking freely about classes, but everything we did could instead be translated whenever we talk abstractly about their existence, or have shown their existence classes and properties. We could always show that the proof is always basically showing that there's a formula that represents that class. Right, so in the notes, I give an explicit formula. Maybe you can look at that in the notes, just as an illustration of that. Okay, so let's have a break and we'll start again at the quarter past. Are there any questions? Okay, so these are the axioms we've been working with in the course, with or without the axiom of choice. If you, incidentally, want to think for yourselves about how you can most simply formulate the axiom of choice in these axioms in this language, this is an interesting exercise to do that. So I didn't used to have this in the notes, so I decided to write down what I thought was the simplest axiom for the axiom of choice yesterday in the notes, so you can find what I think was the simplest axiom. Now, having done it, I decided to ask AI, which is the simplest formulation of the axiom of choice in the first order language of set theory, just using primitives, and it came up with exactly the same formula that I'd written down. So but surprised by that. So,
we won't get replaced.
Sorry?
We won't get replaced yet.
Well, maybe that goes to show I could be replaced. I mean, it was as good as this. And might want to use a fish. Sorry? Might. Oh, goodness me, thank you. Oh. Yes. Sorry. Anyway, so the axioms I've written are good enough for doing what we do in the course, but usually one uses the axioms of Zermelo-Fraenkel theory. That's the standard set theory for mathematics. And I want to use that for the rest of today's lecture as a reference point, because I want to talk about independence results, what's not provable. And in order to talk about what's not provable, one wants to have reference theories that are standard theories that other mathematicians recognise. So I want to now tell you what the axioms of the Mello-Frankel set theory are. But we can take this as a basis and we can just add some more axioms when we get to Mello-Frankel set theory. Does anyone actually know what, have a suggestion for how we might extend this axiomatization here to get to Mello-Frankel? What might we do?
I have a formula right here, and it's even
Are you looking at the notes online?
no,
No.
but it's even like it's not that long, and it's formulated even like in the primitive
So this is a formula for what?
for the axiom first.
Of the axiom of choice. Okay.
I didn't see.
Oh, sorry. The question is now the question is now to what we need to add to this to get to Mello-Frankel set. Yeah.
Sorry.
Okay. So in the Mello-Frankel set here, I've already said everything is a set. So if we starting with these axioms, we add just the axiom that I've been taking the ZF is our axioms plus universally quantified axiom saying everything in a set. And of course, if you've got this axiom, everything is a set, it basically means you don't need the is a set predicate in the language. So of course, in the ordinary formulation of set theory, there is no is a set predicate in the language, just always true. And you can just eliminate all the occurrences of S of X from here. And then you get a quite concise axiomatization anyway in the usual language. Using this nice device of having the quantifier that says there is a set, then you satisfy something, which still makes sense even in the context of ordinary set theory. Okay, so that's one axiom. There's one further axiom that we didn't have from the Mello-Frankel set theory.
Foundation.
The foundation axiom. But the foundation axiom can be formulated in various ways, but basically it says the membership relation on the class of all sets is a well-founded relation. So in other words, if we have any set of sets, and because we're in some other Frankel set theory, a set of sets is just a set, then well, the relation is well-founded. In any set, if any non-empty set, you have a minimal element. So every set should have an element that is minimal in the membership relation. So that's, we can formulate and say this is everything is a set. Let's put the, well, I'm not going to put it plus the axiom for all x that everything is so if x is a set, then if it's non-empty, so if there exists a y such that y an x, then there exists a smallest element in x in the membership relational term. So there again exists a y such that there exists a y in x, smallest in the membership relation. So in other words, such that for all z in x, it's not the case that z belongs to y. If there were, z would be, y would not be minimal. So it's not the case that z belongs to y. So this is everything is a set. And our foundation. And eventually, what this is saying is that the universe of sets coincides with the cumulative hierarchy that we did about 4 or 5 lectures ago. We also looked at in the exercise class following that lecture, and we used it in order to construct the growth of the universe. That was the context in which we saw it. Okay, so that's ZF, but the standard base theory for mathematics is ZFC, which is simply another Frankel plus the choice, which the short axiom in the notes of the axiom of choice, fun exercise. Think about how to formulate the axiom of choice, or you can do that. And of course, it's already done. Okay, so this is considered to be, you ask most mathematicians in the street, what is the foundation of the axiomatic foundation for contemporary mathematics? They will still say, I guess, most of them ZFC set theories, another Frankel set theory with choice. It has a quite small axiomatization. We've managed to fit it in like a word and a half, and that's even doing it in a non-economical way because we've got these set predicates around that you don't need. Although I didn't write the axiom of choice, but that's just one more line. So it's an absolutely remarkable thing that from such small axiomatization that you can essentially prove all the known theorems. All with some, sometimes one needs a slightly more powerful axiom, which we'll talk about a bit later. But it's even amazing actually that in set theory you can basically formulate the whole of mathematics in this very simple language with just one predicate, and obviously you have to do a lot of coding things up in order to be able to do that. But anyway, one can formulate basically the whole of mathematics, and one can prove it from the axiom of set theory. So that's remarkable. And moreover, because we've got this formal axiomatization, we have formal rules of proof, and that means that the whole of mathematics can potentially be done on a computer in a proof assistant, following the formal rules of proof, getting the proof assistant to check the correctness of our reasoning, and just writing out the proofs in full detail, and we can develop our whole body of mathematics in that way. Now, in the age of AI, it's not even so impossible a prospect as it might have once been, because probably an AI can do most of the formalization for us. But the other benefit about having formal axioms is that now we have the notion of, we have a precise set of axioms, we have a precise derivability relation, namely this 10-star relation that I wrote down before. Set of axioms imply, from a set of axioms we can derive a consequence. And it now becomes a precise mathematical question whether a particular sentence that we come up with is provable or not from our set of axioms. So there is as I already wrote, if T is a set of axioms, then we have a precise mathematical relation for a sentence phi. Can we prove the sentence phi from the axioms T? So phi is provable using the precise rules of first order logic. I won't write that part down from T. Because this is now a precise mathematical relation, we can now make sense of the question, what does it mean to say that a particular sentence is not provable? So we therefore also have a precise meaning or phi is not provable. And one of the major topics in set theory in the 20th century, and still continuing to this day, was so set theory was enormously successful in formalizing mathematics, so that the whole of the body of mathematics could be derived from the Axioms of set theory, as we've already discussed. And at the same time, because we've got this precise mathematical question now, those purely set theoretic questions like the continuum hypothesis that we started the course with, we now have a precise sense in which we can ask, is the continuum hypothesis provable or not? And as you know, because we had this in the first lecture, one can show that the continuum hypothesis is not provable, and one can show that also that the negation of the continuum hypothesis is provable.
It's not provable.
Sorry, the negation of the continuum hypothesis is not provable. That is, the continuum hypothesis is independent from the axiom of set theory. And in order to establish this, we need to know how we can establish for a particular chosen sentence, in this case, the continuum hypothesis, that the continuum hypothesis is not provable from the axiom of set theory. So it's interesting to look at this relation being not provable. So in fact, this relation, this is equivalent to a different way of writing this. This is equivalent to, so if phi is not provable, it's the same thing as saying that if we add the negation of phi to the theory, we can't get a contradiction from that. In other words, it's the same as saying that the theory, that we take our axioms T and we add the negation of phi as another axiom, is consistent. Because if we can derive inconsistency from this, well, if we can derive inconsistency from the negation of phi, that's the same thing as being able to prove the negation of phi implies false. In other words, phi, because we're in classical mathematics. So this says not phi is consistent, while T together with not phi is consistent.
And then we assume that T is consistent.
Sorry?
Here we have to assume that T is consistent, otherwise it doesn't make sense.
So for T together with not phi to be consistent, T has to be consistent. Yeah. I mean, this being consistent implies that T is consistent. But this, you don't need to make that assumption in order to take the equivalence between these two things. However, making the assumption that T is consistent is going to be very important, as we're going to see. I don't think it's needed to take these two statements. So using this formulation, I want to precisely state the main results that tell us about the independence of the most important principles which are independent from set theory. So these main results, so the significant examples of consistency proof. Examples of consistency. And they were done in this form. Well, so they're consistency proofs, but they're also not derivability proofs that certain sentences are not provable. The first one was that mathematicians worried about the axiom of choice because it's a very powerful axiom. It has lots of uses. But, you know, unlike, well, we broke the axioms off now, but the other axioms are all saying essentially that certain concretely specified sets, classes, concretely specified classes as sets. The axiom of choice just says says that in certain situations there exists a set that comes out of nowhere and fulfills which fulfills the condition. So mathematicians worried about the non-constructivity of that. So it was a very important result when Gödel proved that, well, not here, he proved that the Zermelo-Fraenkel set theory with choice is consistent, and moreover, also the generalized continuum hypothesis, or sorry, I'm going to put generalized continuum hypothesis in later, but he did. This is the stage piece of work. And prove that ZFC is consistent. Well, actually, to prove anything about consistency, you need to assume something is consistent to begin with, because Gödel has also the same. This is Gödel from the end of the 1930s, but maybe it was published about 1940. Gödel also had what's called his second incompleteness theorem that says that no theory can prove its own consistency. So proving consistency is known to be difficult. But what he showed was that the best thing you can do, well, anyway, good thing that you can do, which is as long as we accept that the axioms of set theory without choice make sense, are consistent, then we can safely add choice to the axioms, and we can't get a new inconsistency from that. Okay, so this goes to Vasily's point. It is important to assume base theory is consistent in order to be able to prove anything is consistent. So you have to assume something is consistent, and the powerful results are when you have something that you're willing to believe in, so hopefully some set theory, and from that you can see that it's safe, also assume choice. So this is the other formulation of this is in Zermelo-Fraenkel set theory, we can't prove the negation of choice.
So I wanted to add to the point that you raised that in order to prove that anything at all, any theory at all is consistent, we have to already assume a consistency of some other theory. But I wonder if this is true. I would expect that this is not true for theories that are too weak to fulfill Gödel's criteria. For example, Frisburger could
okay. Well, that's not. We're talking about. Of course, this is a course on set theory.
Okay,
so that's but
there
are even some very weak theories that prove their own. But they have to be very weak. Okay, but so this says the negation of the axiom of choice is not provable, but it would be consistent. It was still plausible from this result, although nobody believed it. But it was still plausible from this result that the axiom of choice might actually be provable from the other axiom. And actually, it took all the way until this was like I think published around 1940. It took all the way until the 1960s for Cohen to prove that the axiom of choice is fully independent of the Zermelo-Fraenkel set theory by proving that if the Zermelo-Fraenkel set theory is consistent, then also the Zermelo-Fraenkel set theory plus the negation. Okay. So choice is safe. Can't introduce an inconsistency. Also, this negation is also safe. But negation is less useful. Well, actually, I have my own opinions on that, but let's not get sidetracked by those. Okay, so the most famous consistency result in mathematics, the most famous independence result in mathematics is the continuum hypothesis. So that was established by, again, Gödel and Cohen in the same bits of work. So what Gödel showed was that, again, if the Zermelo-Fraenkel set theory is consistent, then it's safe to add not just the continuum hypothesis, but the generalized continuum hypothesis to the axiom. So the negation of the generalized continuum hypothesis is not provable on the axiom. That's the unprovability question. But once again, mathematicians believe that it's not possible to prove. So this is. I might have said something wrong with the negation. This is saying it is. Sorry, the negation is not proved. But this still left open the possibility that the generalized continuum hypothesis might be provable from the axiom. Once again, it took until the 1960s to sort that out, and the expected result was true, that if the Miller-Fraenkel set theory is consistent, then also the Miller-Fraenkel set theory plus the negation of the continuum. So here I'm putting negation of the continuum hypothesis rather than negation of the generalized continuum hypothesis, because negation of the continuum, because we're negating it, negation of the continuum hypothesis is actually a stronger statement than negation of the general hypothesis, giving a very specific way of generalized continuum. And there's something I missed out here, which I should have put in, that actually the results are not just that the generalized continuum hypothesis and the negation of the continuum hypothesis are consistent, but they're also both consistent with the axiom of choice. Okay, so this is again covered in the mid-1950s. So in the case of the axiom of choice, these results are very reassuring to mathematicians, especially Gödel's result, because mathematicians were a bit worried before Gödel proved this about the axiom of choice. It looked so powerful, they weren't sure that it was really safe to use, especially when funny results like the Barnard-Prosky paradox started coming out. Mathematicians really began to wonder, does it really make sense, the axiom of choice? So Gödel's results, together with some other results of giving more information, reassured mathematicians that the axiom of choice really is safe to use. And so from this point onwards, but maybe even before that, mathematicians wanted to add the axiom of choice as an axiom to set theory because it's very useful in mathematics and because they can see that it is not going to cause any harm. On the other hand, with the continuum hypothesis, again, the continuum hypothesis, and even the generalized continuum hypothesis, is harmless. We can safely add it. It could tidy up some mathematical arguments. There are some places in maths that it's known that some consequences hold if you have continuum hypothesis. But still, mathematicians don't want to add the continuum hypothesis or its negation as an axiom, because unlike with choice, in which one can have a mental picture in which you understand, okay, well, we've got a family of disjoint sets, non-empty disjoint sets, and we're picking out a single member for each of them. That seems like quite a nice, as a set, that seems like quite a nice intuitive thing to do. Whereas the question whether the continuum hypothesis holds or not doesn't really have any sort of compelling truth to it, because people haven't seen good reasons to see it as being true or false. So these axioms, so continuum hypothesis is generally not added as not true. It's not considered as a truth. But it's then interesting to know that it is independent. So what I want to talk about briefly is a little bit about what technology is used to prove these theorems, because that's so these were very innovative results in mathematics. So Cohen was awarded the Fields Medal in 1966, the same time that Grothendieck and Michael Atiyah also won the Fields Medal. Cohen won it, so this is like one of the main prizes in mathematics, Owen won it for this proof, introducing a very novel technique. So how do we prove such implication? So obviously I'm going to be very sketchy about this because one can't give very much information without having several lectures on it. The main way that the proofs came about is in mathematical logic, one can understand consistency for a theory. So Gödel proved his incompleteness theorem, but he also proved a completeness theorem, first order logic. And by Gödel's completeness theorem, the consistency of the theory is the same thing as saying that the theory has a model. So one writes this in symbols like this. There exists a mathematical structure that is a model of theory taken. And so an implication of this form, so to prove, we want to prove an implication that if T1 is consistent, then T2 is consistent. But to prove that, what we do is, well, T1 being consistent is the same as having a model of T1, and T2 being consistent is the same as having a model of T2. This gives a natural recipe for doing this kind of proof, which is give a way of constructing from a model of T1, manipulating the model in some way to manufacture from a model of T1, find a way of, from a model of T1, manufacturing a model of T2. So give a construction of a model of T2 from any given model of T1. And you can see just from this, from general recipe, how useful the left-hand consistency assumption is, because it gives you a model to start with, so you can make your construction of. You don't have to manufacture your model out of thin air, which you can't do because of Gödel's second incompleteness theorem. So how this works, I'm going to talk about Gödel's result for this one. But in fact, we can bunch the two results together. So Gödel's proof of if ZF is consistent, then so actually what he proved, he did everything in one go. He proved that if ZF is consistent, then so is ZF extended with choice and the great generalized continuum hypothesis altogether. Oops. Okay, actually, so this is exactly that's written here. So we start with a model of the Mello-Frankel set theory. So what Gödel found is, so this is like a model of the universe of sets. We think of it as a model in the sense of mathematical logic. It's going to be a set itself, but it's a set that we can view as a set of all, as a set from the meta theory of a collection of elements that satisfy all the axioms of set theory, and it's got a membership relation working on it. So there's a model in which all the axioms of the Mello-Frankel set theory hold. And he showed a way of cutting this model down to a smaller model consisting only of those sets in this model that are constructible in a certain transfinite sense from ordinals. It's a very involved definition, although quite a natural one. So I'm not going to say how it works, but you extract a smaller, what's called an inner model, which works inside M. Let's call it curly L, consisting of, so the elements of this model are all the sets in the model, so to speak, the universe of all sets of that model, and we take out only those sets that are deemed to be constructible according to this recipe that Gödel had for constructible nature. We take out a sub-universe of constructible sets in the sense of Gödel. That's constructible set. And it turns out that so there's actually a formula in set theory that expresses what it means to be constructible. So there is a class of constructible set. Constructibility expressed by a formula. So there is a class L of constructible set. And it can be proved in set theory. There's another formula that defines a well-ordering. So L has a definable well-ordering. And because of this, the model curly L satisfies choice, because whenever you have a family of non-empty disjoint sets, you can pick out a representative from each set as representative set for a set of representatives for that family of sets, merely by always taking the least one in the definable well. So hence, L satisfies the excellent choice. It also satisfies the generalized continuum hypothesis, but for much deeper, so for reasons that aren't so easy to explain. So this L, this constructible universe, in general satisfies Gödel's another axiom, which is called Gödel's axiom of constructibility. Which says every X is in L. So all sets in the universe belong to L. And this is normally written as V equals L, because V is the transfinite hierarchy, which in ZF set theory is just all the sets of the universe. But this basically says every set is L. So this is a famous axiom in set theory, and Gödel actually briefly thought maybe this is a good new axiom to add to set theory, because it settles so many questions. It proves the axiom of choice, it settles the generalized continuum hypothesis. But then he realized from a sort of truth point of view, there's absolutely no reason at all to believe your universe set every set should be constructible, which is quite a fussy definition. Yes.
What is I'm not sure what is a constructible set.
Yeah, okay.
Will we get to that or not?
No, this is the level of detail I'm going to go.
Okay.
I mean,
that's good.
That would be a whole lecture. Well, to define a constructible set would be a whole 1 hour lecture. Do anything with it to get these results would be more than a 3 hour lecture. That's a U or a V? Sorry? That's a V. Because, well, we're in ZF set theory. So the universe of everything is the same as V, which is the cumulative hierarchy. So it could be a U as well, but this is the way you normally see it written. Okay, so that's Gödel's result. So what about Cohen's result? So Cohen, this was a very deep result. I mean, it took him, as I said, until the mid-60s to do this. So Cohen showed how to, from consistency of Zermelo-Fraenkel set theory, get consistency of Zermelo-Fraenkel set theory with choice, here, and the negation of continuum hypothesis. So let me briefly say that, and then we'll have the last thread. So what's one thing that's nice about it is it works in somehow the opposite direction of Gödel's proof. So Cohen's proof of if ZF is consistent, then ZFC plus the negation continuum hypothesis is consistent. Okay. So we can start off with a model of Zermelo-Fraenkel set theory. But in fact, because we've already proved, or Gödel's already proved that if ZF is consistent and ZFC is consistent, we can actually start off with a model of ZFC, which we need to do here. So we'll take a model of ZFC by a famous result in logic called the Levenheim-Skolem theorem. You can actually start off with a countable model of ZFC. And to make things convenient, we'll start off with a countable transitive model of ZFC, which means that the membership relation in the model, which means the model is just a countable collection of sets, it's just a countable set in the real world, and the membership relation in the model is the actual membership relation. Then there's a little bit of cleverness needed at the end of the proof to get rid of this assumption of having a what's I call the transitive model, but let's not get into that. But we start off with a countable transitive model of that here. Okay, so for those of you who haven't done a formal logic course, one of the puzzling things in logic is this Levenheim-Skolem theorem, which says that the axioms of set theory, if they have a model at all, then they have a countable. That's weird because the axioms of set theory can prove that the existence of uncountable sets, such as the real numbers, and our set of the natural numbers. But still, you can have a countable model from the point of view of the real world that you're working in. It's just from the viewpoint of inside the model, there are sets that are uncountable according to the logic of the model. They're countable in the real world, we can see they're countable, but the bijection between that set and the natural numbers does not exist as a set, as a function in the model. So that's how we can find a countable model, and there's a theorem that tells us we can get one. That's why it's not inconsistent to have a countable model set. However, suppose we've got a countable model. Yes, we've got a model of ZF. So ZFC here. So we start with a model of ZFC because although we presume consistency of ZF, we've already got Gödel's result that implies the consistency of ZFC, so we can use that, and we actually need to have a model of ZFC. That's how we get this need to fill hold with the. So the construction I'm going to very briefly outline advice on starting with the model of ZF. Okay, so it's a countable model. So that means when we look at the set omega 2 in the model, so that's the ordinal LF2 in the model M, it's countable. And when we look at the power set of the natural numbers in the model, it's also countable. So in the real world, there exists a bijection between omega 2 and the power set of the natural numbers in the real world. That bijection is not in the model. Does not exist as a function in the model, because otherwise the model wouldn't work. But it's still there in the real world. What we do is we extend the model M by putting one of these bijections. Well, actually, we only need to put an injection in. So there exist in the real world injections from omega 2 from the set in M that models omega 2 to the set that models the power set of natural numbers. We're going to throw in one of those injections, and Cohen found a way of finding an injection that's suitably generic, but if you throw it in, it basically amounts to extending the model with an injection and not mucking up too much else at the same time. In such a way that basically the language of set theory can only tell that it's an injection, and what follows from it being an injection, nothing more than that. So this is how one does this. Is very technical. It's a technique known as forcing. But what you do is you force an injection from omega 2. So let's write injections like this with a hooked arrow from omega 2 to the power set of n. So this is omega 2 interpreted in the model n, with the power set of n interpreted in the model of n, into a new model n prime, which we define to be n extended, let's call this injection I. So basically, this model is written like this. We start off with the model n, and we force the injection I into it. And then we look at what this gives us. And so then, in the new model n prime, we have, well, we still have the initial ordinals from the model m. So this is omega 0 or omega. And that's still by a quite combinatorial argument. The strict cardinal inequalities are preserved in this construction. So this is less than omega 1, and this is less than omega 2. But because we threw this injection from the real world into the model, now in the new model, the cardinality of omega 2, because we have the injection I here, is less than the cardinality of the power set of the natural numbers. Well, but actually, it's the power set of natural numbers as interpreted in the original model M. But because we've thrown a new set in, the power set of natural numbers is now going to be in the new model. Well, we've added new things to the model, so the power set of natural numbers in the new model is going to be larger. So again, we have a cardinal inequality here between the power set of the natural numbers interpreted in the new model M prime. But in any case, what we see we've done is we've managed to construct a model in which now our power set, so this is the power set of natural numbers here, is larger than omega 2. And therefore, the power set of natural numbers has a beta cardinality Alex 2, and therefore the continuum hypothesis. And as well as just justifying the whole forcing thing, two other very tricky points for proving that actually adding the new generic function in here doesn't allow us to give some bijections going back in these directions. So these remain strict inequalities. That's quite a technical argument for that. And another argument is needed to show that this model still satisfies the absolute choice. All that works, and that's how the proof works. The beautiful line of argument that so actually Cohen was an analyst working on the Riemann hypothesis, amongst other things, but he got interested in mathematical logic, and so basically teaching himself, he came up with this very impressive piece of work. Okay, so it's 2 minutes past, well, 3 minutes past 4, but I guess we'll start again at 4 past. Any questions? Right, so okay, so I've discussed a little bit about independence results and about the technology used to show them. And the independence results we've seen so far are all safe independence results, in the sense that if we believe in the consistency of the base theory, the Zermelo-Fraenkel set theory, then we get the consistency of all the other theories we're talking about. So we just need to have faith in the original axioms. But there are other consistency results that are not safe in the same sense. And this is the kind of consistency results that you get when you're talking about principles that have additional power in them, like the existence of large cardinals. So let's have a look at, I mean, we did measurable cardinals last week, but let's look at what the situation is for inaccessible cardinals that we covered a few weeks ago. So let's look at consistency results of inaccessible cardinals. And one can show that if ZF is consistent, then one doesn't need to assume anymore to show that ZF together with the negation of a weakly inaccessible cardinal. So here WIC is there exists a weakly inaccessible cardinal. And we're going to have SIC, which is there exists strongly. Now, if ZF is consistent, it's consistent that there is no weakly inaccessible cardinal. I did this one because that's the better result than saying system that there's strongly inaccessible cardinal. If there's no weakly inaccessible cardinal, then there's certainly no strongly. Of course, strongly inaccessible cardinals are more interesting. So how do we get the consistency of a strongly inaccessible cardinal? Well, we can prove that we cannot prove this from the consistency of the Zermelo-Fraenkel set theory. Because if we had a strongly inaccessible cardinal, if you have a model with a strongly inaccessible cardinal, then, if you have a strongly inaccessible cardinal in your universe, you can consider the set of all sets of cardinality strictly less than that strongly inaccessible cardinal, and that you can prove that that is a model of set theory. Therefore, if you have a strongly inaccessible cardinal, you can prove the consistency of the Zermelo-Fraenkel set theory, and therefore by Gödel's second incompleteness theorem, we cannot prove the consistency of this theory on the assumption that the Zermelo-Fraenkel set theory is consistent. So in fact, there is an interesting result here, which is that in order to prove the consistency of a strongly inaccessible cardinal, it's enough to assume the consistency of a weakly. But you can't really do better than that. And with strong cardinals, there's always this flavor of large cardinals, rather. So there's always this flavor of somehow there's no real way of proving the consistency of the theories without essentially assuming something as powerful or close to being as powerful as the property that you're trying to prove. So in other words, we might believe the axioms of the Zermelo-Fraenkel set theory, but if we want to add a strongly inaccessible cardinal to it, we need a leap of faith. We need to really just believe that they're consistent. I mean, the Zermelo-Fraenkel set theory already involves quite a faith in it because we're already believing in quite large things. And as you go up, say measurable cardinal, like we studied last week, you need to put more faith in it. So, you know, my belief about these things is that if the concept seems natural and meaningful and nobody's found a contradiction from it, and there seems to be a coherent picture of mathematics from it, then I'm happy to put my faith into it for the moment. But if somebody eventually proves it's inconsistent, I'll just sort of retract that bit of faith and go down to something more manageable. But anyway, so it's a good question, sort of how do we believe in these theories or not? And we somehow, for large cardinal axioms, you need to essentially assume a large cardinal axiom that you need to assume because. So there's a question then: why would we, what leads us to believe in such axioms? Why would we consider them? So people do like to add such axioms to set theory. And essentially, both for these axioms and for other kinds of axioms, there are two motivations two forms of motivation that one might consider. Motivation of large cardinal axioms and other strong principles. And these are called the intrinsic and extrinsic. And the intrinsic is, you look at the axiom and you see that it's stating a believable property in its own right. So you accept the axiom on account of its own plausibility, let's say. Plausibility and coherence and so on. The extrinsic one is that you might accept the axioms because they seem to provide a natural basis for proving results that are good results and make sense. So they might have the axioms have mathematical consequences that are believable. So extrinsic is accept axioms on account of their good consequences. I want to give an illustration of this kind of thing, which is an axiom that nowadays, not in our original list of axioms, which is an axiom that most set theorists nowadays believe should be added to the axioms of set theory as a correct axiom, an axiom of true mathematics. And this goes back to what we were doing last week. So last week, we did measurable cardinals, and we had Martin's determinacy result for what I was calling analytic games. So we had that if a measurable cardinal exists, which I'll write as MC, I'm not quite sure what the standard abbreviation for it is. But anyway, here I mean there exists a measurable cardinal. And we saw that I told you, we didn't prove it, but measurable cardinal implies that analytic games are determined. So I just write analytic determinants. This is every Gale-Stewart game, these infinite two-player games, where the goal set is an analytic set, so a continuous image of a Borel set. Every such game is determined. And we got that from the measurable cardinal. And moreover, I mentioned the kind of consistency converse to this, which we can now write down formally. And the consistency converse is that if ZFC plus analytic determinacy, I'm not going to write AD because that's the full axiom of determinacy that's incompatible with the axiom of choice. So if analytic determinacy is consistent, then ZFC plus the measurable cardinal is consistent. So this already gives a kind of an example of what I was saying, but whether or not one should have a measurable cardinal, that's a massively enormous thing. I don't know. Most set theorists take this as a reason for believing that analytic determinacy is a truth of mathematics. Analytic determinacy is just a result about subsets of bare space. So it's a very low level in the set theoretic hierarchy. It's a property of subsets of bare space. We can prove that we can believe it's true because we can see how we can prove it in a sensible mathematical way from some concept that makes sense to us, some very large cardinal. But we might not want to insist that such large things exist in the world. But still, we've got enough evidence to believe that the theorem of analytic determinacy is actually true. So this is like essentially I don't know if it's, well, in a sense, it gives us an extrinsic justification for believing in measurable cardinals, the fact that we can prove analytic determinacy. And maybe the acceptance of analytic determinacy, I don't quite know how it falls into this categorization, but still, it's based on the fact in respect to the figures I've said. So in fact, set theorists push this quite a lot further. So the analytic set, remember when we did the Borel set a few weeks ago, we had this hierarchy where we started with open sets as sigma 0, 1 sets, or sigma 1, we wrote that there's a 0 superscript that we were omitting, and closed sets of pi 0, 1 sets, and then we sort of closed things under countable unions and countable intersections that have this transfinite hierarchy of sigma and pi sets. Then you get all the Borel sets in this way. And we're now going to define a new hierarchy where instead, for the next step, instead of closing under countable unions or countable intersections, we're going to take continuous images. Or another way of calling them is projections, which I'll use that word. I'll explain what it means in a moment. But this time we start off with the Borel sets if we want them. We're going to project them to give us sigma 1, 1, which is the analytic set, so continuous images of Borel set. And pi 1, 1. So we now have a superscript here, and again, we're going to go up the hierarchy. We're just going to use natural numbers this time in the hierarchy. We're going to go up the hierarchy again in the lower index. So this is complements of analytic sets, and such sets are called co-analytic sets. And once again, if we take continuous images of, or at least measurable images of co-analytic sets, we go beyond co-analytic sets and we go one step up the hierarchy. But the way this is normally written is to go up the hierarchy, so to go to level n plus 1, we define sigma n plus 1 to be what is called projections of pi 1 n set in, so we consider bare space times we're looking at subsets of Polish spaces. So we're defining what it means to be sigma 1, 1 in any Polish space. It means an analytic set and that Polish space. So in the Polish space X that we're looking at, we can take the product Polish space. And the projection here is we have a pi1n set in here. By projecting it, we consider the image. So B is the pi11 set here, the pi1n set here. We project it along the second projection down to X, and we get the image I2B, which is a subset of that. The technical details don't really matter because this is not examinable material. And I just want to give you a flavour of it. And so the sigma sets, we project the pi sets, and the pi sets, we project the sigma set. But another way of considering it is we're taking images of pi sets, images of projections or sigma 1n. And this gives us a hierarchy index. As I said, the lower numbers indices are in the natural numbers, and a set is projected if it is with some sigma 1n somehow. It's the same as being in some pi 1n because each sigma 1n is contained in pi1n plus 1 and so on. Yes?
So you define this just for natural numbers?
Yeah, just for that. Well, because you only need to define the natural numbers. So if you take, we're applying this single operation. So if you take the collection of all subsets at the end, then they are closed under the collection we get is already closed under projections. So basically, if we tried to continue it, we would find that we've actually stopped at this point. Anyway, it's just a collection of a richer class of sets. Each sigma 1 n plus 1 is strictly larger than each sigma 1 n. And the important result, which was a major result in set theory, is known as projective determinacy or projective determinacy. Projective determinacy says every projective game. So a game with projective goal set, projective Gale-Stewart game is determined. But of course, we can't prove this in ZFC because even to prove that analytic sets are determined, we needed a large cardinal, specifically a measurable cardinal. Analytic sets are just the first step here. So what do we need? Well, we need IWC, which is there are infinitely many wooden cardinals. So Hugh Woodin is a professor, I think, at Berkeley in California, or probably emeritus by now, but he's you ask anyone set theory who's the guru of large cardinals, Hugh Woodin is the guru of large cardinals, and he defined his own version of large cardinal. And if you need infinitely many of them, but if you have infinitely many Woodin cardinals, but I don't know what the definition of a wooden cardinal is, something quite hairy. But if you've got infinitely many of those, then that's a projective Gale-Stewart game. No. By the way, this is now our
fourth determinacy result mentioned. So we had the one we actually proved in matches was every closed set is determined. That was proved by Gale and Stewart in their paper on Gale Stewart game. Then we have every Borel set is determined, which is the landmark result in set theory. That's provable in ZFC, and that was proved by Tony, people call him. It was proved by Tony Martin. So Martin's determinacy result. Every Borel set is determined. Then we have every analytic set is determined. This was also proved by Tony Martin. And then we have this result, which is that every projective set is projective game is determined. We have infinite many wooden cardinals, and this is also proved by Tony Martin. Okay. Martin is the guru of the determinacy results, but this result was together with Field as well, so we had a collaboration on this. And moreover, just as in the case with analytic determinacy, this use of large cardinals is in a sense necessary, in that we can prove, and it's the best reading we can prove, we can prove that if ZFC plus projective determinacy, PD, this is PD, is consistent, then ZFC plus infinite the existence of infinitely many wooden cardinals is. So we're now massively up in the stratosphere of large cardinals. But nonetheless, the result we're getting is still a quite down to earth result, in that it is still just a result about these simple two-player games and subsets of their space. So sets of infinite superfluid. And because of this nice interplay between conceptually believable world of large cardinals and nice combinatorical results in the sense about in an infinite percent about games, set theorists believe that this is the truth of mathematics. The projective determinacy is truth. So,
excuse me, just before you run out. It's okay, it's okay. So, just two questions here. Short questions. So, the first is, so analytic sets and co-analytic sets are subsets of which set? That would be the first question. The second question would be.
So there are some. We have a Polish space, and they're subsets of a Polish space, and we're defining this for any Polish space. So for any Polish space, and simultaneously for all Polish spaces. So for any Polish space X, we know what it means to be a Borel set. And an analytic set is an image of a Borel set under continuous, with a continuous function from their space. That was how we defined it last week. So we know what this notion is in any Polish space at all. So the thing is, here to understand sigma n plus 1 in the space X, we use the notion of pi 1n in this space.
Yeah, so that's
so there is a change of space there.
Yes, so that's the point that's not clear to me. How we can change the space.
Well, because for each n, we define simultaneously for all Polish spaces what it means to be a pi sub 1, a pi 1 n, and a sigma 1 n subset. In every Polish space. So by the time we get to n plus 1, we've defined what it means in every Polish space, and this is actually the Polish space and their space is a Polish space. The product is a Polish space. Okay.
And projective Gale Stewart game is just a Gale Stewart game on
a Gale Stewart game in the usual sense. So the goal set is a subset of n to the n, and we're asking for that goal set to be projective.
Okay.
So many set theorists consider PD, projective determinacy, is considered to be a missing axiom from set theory. From ZFC. It's still about small sets. It's not forcing us to believe in the existence of any monstrous things like William cardinals. Monstrous in the terms of size, not in terms of the negative connotations, the monstrous in that case. But anyway, yes. You can add it as an axiom to the set theoretic axioms you use in everyday life if you want to, but maybe you're not going to find very many uses for it. Yeah.
So are within cardinals much larger than measurable?
They're much larger than measurable.
So you could say that if you believe in projective determinacy is in fact true,
yeah,
then you believe that there is a world somewhere there, or I could say a model that.
Yes,
yeah.
Indeed. Yes. That's a consequence of justification. So this raises the question of why should we believe the axioms of set theory in the first place? And what should we take? What should we take as what should we expect of our axioms? And so I've written some remarks on this in the notes, but I don't think I want to write it down here. But basically, I asked the question, so we're working with the axioms of set theory, in what sense do we really believe that they're true? And this is just a question in the philosophy of mathematics. Do you want to believe they're true, or just that they're somehow practically useful? But at least they present a coherent picture. They certainly seem practically useful. We can do mathematics. They present a coherent picture. But it is worth thinking for yourselves about where you want to place the boundary between what you believe to be actually true, what you believe to be just kind of convenient and probably consistent. Maybe you believe the whole of the axioms of set theory are true. Maybe you even believe that projective determinacy is true. I don't know. But you can at least start thinking about things like properties of natural numbers, just expressed by quantifying over natural numbers. Do we believe they are objectively true or false? That's not so hard to come to believe that. And the next step up would be to look at real and complex numbers. The properties of real and complex numbers necessarily true or false. I was going to say it's the Riemann hypothesis, actually in the notes. So there's the example of the Riemann hypothesis. So we don't know whether it's true or false, but is it necessarily true or false? But actually the Riemann hypothesis is equivalent to a sentence in first order number theory in any case. So in a sense, we know that if you believe in number theoretic statements to be true or false, whether the Riemann hypothesis you should also be true or false. So that's if we have properties of numbers, properties of natural numbers, properties of real numbers, which is like properties of real number. The real numbers are isomorphic to the set of subsets of the natural numbers, so it's basically the same as properties of effects of natural numbers. So maybe things there, either true or false. So then the next step up is properties of the power set of the power set. The properties of sets of numbers, and this already takes us to the continuum hypothesis. So at this level, myself, I find it hard to believe. I don't really believe the continuum hypothesis is either true or false. I mean, I know some models in which it's true, and I know some models in which it's false. And for me, there are somehow different conceptions of set that are all okay, and some of them the continuum hypothesis is true, and some it's false, and in others, even with that conception, etc. The notion. But in any case, I just encourage you to think about these things for yourself, because, yeah, ultimately we're doing maths from the whole of the subject of maths is based on this axiomatization. I mean, it can be derived from this axiomatization. A lot of it doesn't rely on the full pair of set theorem. There is a sort of deep question, just why does it all work so well? And that's a beautiful thing that it does. So I'll end with these thoughts and let you continue these thoughts in your own way. So are there any questions? Yes, Vasilia?
Isn't it just better to believe what some smart set theory believes? Because we know less theory.
But it's very hard to find two smart set theorists that believe the same thing. Although a lot of them believe in projective determinacy. But the finer details, they have a lot of, they don't all believe the same thing. But yeah, if you want to, but you know, I'd like to think things through for myself. But that's a good point. Yeah, if you like to believe authority, then so okay. Other questions?
Maybe do you know, are there any like actively considered models of set theory where projective determinacy fails, and like they're interesting?
Yes, so projective determinacy fails in the constructible sense. And in fact, even fails very low down. I think maybe the analytic sense still determined in the real world. I'm not sure. But I think the next level up. Yeah, it's a good question.
And will be also any other sort of missing axiom candidates in the sense of like from that original essay like he was linked, it was mentioned exactly as like he should consider new axioms by their power, which would help us.
Okay, there are various interesting axioms. So there's so related to the continuum hypothesis, people sometimes want axioms there. So Gödel, well, he believed to some degree that continuum was LF2, but actually he wanted it to be derived from other properties. There's an interesting axiom called Freiling's axiom of symmetry, which is sort of measure theoretic. Freiling's axiom of symmetry is a kind of measure theoretic based axiom or influenced axiom, and this axiom proves the negation of the continuum hypothesis follows from this axiom. Now, people don't tend to really believe this axiom is true, but it's an interesting thing.
I have a remark on this also. I remember a lecture, I think, by Mario Carnero about, well, in it he mentioned that Lean, so the theory of Lean, the group system, is equiconsistent with ZFC plus count of remaining. I don't remember.
Strongly accessible.
I don't know. I don't recall if they were like weakly accessible, strongly accessible, or just last. Okay, okay. So then you remember better.
Oh, I don't at all. Yes.
So, yeah, that's like Lean people make that basically make that.
So the thing about type theory is one often considers type theory having universes in it, and universes in type theory is very similar to a Grothendieck universe.
Yeah.
In set theory, particularly in the context of Lean, where you have the law of excluded middle, people are often using the law of excluded middle. So I think in that sense, it's basically basically the same thing. That's probably that type theory is also equiconsistent with. So it's infinitely many strongly accessible cardinals, but it can even be viewed in a nicer way, which is it satisfies Grothendieck's axiom. Oh yeah, so this is a nice axiom that people like to take as an axiom of set theory. Grothendieck's axiom that every set is contained in a Grothendieck universe. So that's a good one. And maybe I should also mention. Sorry, I had a pointer for this earlier a couple of weeks ago. So also this axiom of broad infinity by Levy. So that's a very nice paper, and also he makes a very good case. It implies some logic. It implies Grothendieck's axiom, so it's a bit more powerful. But again, existence of large cardinals, that he gives a good case for this being a plausible axiom of set theory. So I like this work very much. So I'd like to advertise it. While I'm in the so the final thing, while I'm advertising other interesting work, something I forgot to do, apart from the course, and I put the link to the web page. People who took my logic course last year will have seen this, but there's a very nice book on essentially on mathematical logic with a story involved that includes chapters on it to do with set theory and large cardinal axioms and things like this. So this is in the context of an adventure story, and it's called Castles in the Air. By John Longley. And I'll put a link on the web page. And if the foundations of mathematics interest you, and you also like to see the foundation of mathematics work into a novel format. Novel not being new in this case, but novel like a written novel, a book with a story in. Then I strongly recommend this book. As I say, I'll read it. Okay, good. Yeah.
If you want at this point, I have a remark, but you can shut the recording.
Oh, okay. So in that case, let's do that. Your remark will be lost to future generations, but